Here's a detailed overview of each planet in our solar system, expanding on their characteristics, exploration history, and scientific significance. Mercury. Mercury is the smallest and closest planet to the Sun, making it one of the most extreme environments in our solar system. Its surface is heavily cratered, resembling the Moon, with large temperature variations due to its lack of atmosphere. During its daytime, temperatures can soar up to about 800 degrees Fahrenheit, 427 degrees Celsius, while at night, temperatures plummet to around -290 degrees Fahrenheit, -180 degrees Celsius. Mercury's iron-rich core is unusually large compared to its relatively thin mantle and crust, suggesting it may have undergone significant geological evolution early in its history. Despite its proximity to the Sun, Mercury has water ice in permanently shadowed craters at its poles, where the Sun's heat cannot reach. This discovery was made by NASA's Messenger spacecraft, which orbited Mercury from 2011 to 2015, providing detailed maps and data on its surface composition, magnetic field, and geology. Mercury's surface is marked by vast plains, cliffs, and ridges formed by tectonic activity, indicating its dynamic past. Future missions, like Baby Colombo, a joint mission by ESA and JAXA launched in 2018, aim to further study Mercury's magnetic field and geological history. Venus. Venus is often called Earth's twin due to its similar size and composition, but it has developed into a radically different world. Its thick atmosphere is composed mainly of carbon dioxide, with clouds of sulfuric acid droplets that completely obscure its surface from view. The atmosphere creates a runaway greenhouse effect, trapping heat and making Venus the hottest planet in our solar system, with surface temperatures averaging around 900 degrees Fahrenheit, 475 degrees Celsius. This intense heat and pressure would crush and melt most spacecraft that attempt to land on its surface. The Soviet Union's Venera program in the 1970s and 1980s successfully landed several probes on Venus, providing the first images and data from its surface. These missions revealed a harsh landscape with volcanic plains and rocks shaped by high temperatures and pressures. Venus geology includes large shield volcanoes like Mont Mons and Tesserae terrain, possibly indicative of past tectonic activity. NASA's Magellan mission in the early 1990s used radar to map the planet's surface in detail, uncovering volcanic structures and evidence of recent volcanic activity. Future missions, such as NASA's Veritas and ESA's Envision, aim to further explore Venus' surface and atmosphere using advanced radar and spectroscopic techniques to understand its geology, history of water, and potential for past or present life. Earth. Earth is the only planet known to support life. Its surface is 70% covered by oceans of liquid water, which along with its moderate climate, make it uniquely suited for life as we know it. Earth's atmosphere consists primarily of nitrogen and oxygen, with trace amounts of other gases that support weather systems and protect life from harmful solar radiation. The planet's active geology results in a constantly changing landscape shaped by processes such as plate tectonics, erosion, and volcanic activity. Earth's diverse environments, from polar ice caps to tropical rainforests, support a wide variety of life forms, ranging from microscopic bacteria to complex organisms like plants, animals, and humans. The study of Earth's climate, oceans, and ecosystems is crucial for understanding how life interacts with its environment and how human activities impact the planet's natural processes. Earth's exploration history includes numerous satellites, probes, and spacecraft that have studied its atmosphere, landforms, oceans, and climate. Satellites like NASA's Terra and Aqua provide continuous monitoring of Earth's surface and atmosphere, helping scientists track changes in climate, land use, and natural disasters. The International Space Station, ISS, serves as a platform for scientific research in Earth's orbit, studying phenomena such as weather patterns, ocean currents, and the effects of space weather on our planet. Mars, often called the Red Planet due to its rusty reddish appearance, has long intrigued scientists as a potential place for life beyond Earth. It has the largest volcano in the solar system, Olympus Mons, and a vast canyon system called Valles Marineris. Mars has polar ice caps made of water and carbon dioxide, and its surface features include impact craters, valleys, and ancient riverbeds, suggesting that liquid water flowed on its surface in the distant past. Exploration missions have revealed evidence of minerals that form in the presence of water, hinting at the possibility of microbial life or habitable environments in Mars history. NASA's Mars rovers, such as Curiosity and Perseverance, have explored the planet's surface, analyzing rocks and soil samples to understand its geology and search for signs of past life. ESA's Mars Express and the joint ESA/Roscosmos ExoMars missions have studied Mars' atmosphere, surface composition, and subsurface to uncover its geological history and potential for life. Mars remains a focus of future exploration, with plans for sample return missions to bring Martian rocks and soil back to Earth for detailed analysis. NASA's Mars Sample Return Mission, in collaboration with ESA, aims to collect samples from Mars' surface and return them to Earth by the late 2020s, providing invaluable insights into the planet's history and potential for life. Jupiter. Jupiter is the largest planet in our solar system, with a diameter more than 11 times that of Earth. It is composed mostly of hydrogen and helium, with a small rocky core at its center. Jupiter's atmosphere is characterized by alternating light and dark bands of clouds, caused by powerful jet streams and storms. The Great Red Spot, a giant storm larger than Earth, has been raging for centuries. Jupiter's strong magnetic field creates intense radiation belts and auroras around its poles. The planet has a diverse system of moons, including the 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, each with unique characteristics ranging from volcanic activity to possible subsurface oceans. NASA's Juno spacecraft, launched in 2011, has been studying Jupiter's atmosphere, magnetosphere, and interior structure since entering orbit in 2016. Juno's observations have provided new insights into Jupiter's deep atmosphere, polar regions, and magnetic field, shedding light on its formation and evolution. Future missions, such as ESA's Jupiter Icy Moons Explorer, JUICE, and NASA's Europa Clipper, aim to explore Jupiter's icy moons, studying their subsurface oceans, geology, and potential for habitability. These missions will build on discoveries made by previous spacecraft and advance our understanding of Jupiter's role in shaping the solar system. Saturn. Saturn is known for its stunning rings, which are made up of countless particles of ice and rock ranging in size from dust grains to boulders. The rings are held in place by Saturn's gravity and are thousands of kilometers wide but only a few tens of meters thick. Saturn itself is mostly composed of hydrogen and helium, with a dense atmosphere of ammonia and methane. Its rotational axis is tilted similar to Earth's, giving it seasons as it orbits the Sun. Saturn has numerous moons, including Titan, the second largest moon in the solar system, with a thick atmosphere and lakes of liquid methane and ethane on its surface. Enceladus, another moon of Saturn, has geysers that shoot water vapor and icy particles into space, hinting at a subsurface ocean and potential for life. NASA's Cassini spacecraft, which orbited Saturn from 2004 to 2017, provided unprecedented views of the planet, its rings, and moons. Cassini discovered methane lakes on Titan's surface, studied Enceladus geysers, and explored Saturn's atmosphere and magnetic field in detail. The spacecraft ended its mission with a dramatic plunge into Saturn's atmosphere, sending back valuable data until the final moments. Future missions, like ESA's Comet Interceptor and NASA's Dragonfly, aim to explore Saturn's moons further, studying their composition, geology, and potential habitability. These missions will build on Cassini's discoveries and advance our understanding of Saturn's diverse moon system. Uranus. Uranus is an ice giant planet that rotates almost on its side, with its axis tilted nearly parallel to its orbital plane. This unusual orientation may be the result of a collision with a large object early in its history. Uranus has a bluish-green color due to the presence of methane in its atmosphere, which absorbs red light and reflects blue-green light back into space. The planet is mostly composed of hydrogen and helium, with a significant amount of water, ammonia, and methane ice in its atmosphere and interior. Uranus has a faint system of rings and a set of 27 known moons, including Miranda, which has an unusually varied and complex surface. NASA's Voyager 2 spacecraft flew by Uranus in 1986, providing the first close-up images and data of the planet and its moons. Voyager 2 discovered previously unseen moons and studied Uranus' atmosphere, magnetosphere, and ring system. The spacecraft's observations revealed a turbulent atmosphere with winds reaching speeds of up to 560 miles per hour, 900 kilometers per hour, and a complex magnetic field tilted at an angle to its rotation axis. Future missions, such as ESA's L-class mission Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, aim to study Uranus' atmosphere and composition in more detail. Ariel will use spectroscopic techniques to analyze Uranus' atmosphere and study its climate, chemistry, and atmospheric dynamics. International Space Station. The International Space Station, ISS, is a remarkable collaborative effort among multiple space agencies, serving as a microgravity laboratory and a platform for international cooperation in space exploration. Here's a detailed overview of the ISS. Construction and structure. The ISS is the largest human-made structure in low Earth orbit, measuring about 109 meters, 358 feet, end-to-end, roughly the size of a football field. It orbits the Earth at an altitude of approximately 400 kilometers, 250 miles, and travels at a speed of about 28,000 kilometers per hour, 17,500 miles per hour, completing an orbit roughly every 90 minutes. Modules and components. The ISS consists of multiple interconnected modules, laboratories, and docking ports contributed by various space agencies. The core modules include the Russian segment, Roscosmos, the American segment, NASA, the European Space Agency, ESA, and the Japanese Aerospace Exploration Agency, JAXA. These modules provide living quarters, research laboratories, and operational facilities for crew members. Truss structure. The ISS includes a large truss structure that supports its solar arrays, radiators, and communication systems. This truss system extends along the length of the station and provides structural support while allowing for the attachment of additional modules and experiments. Purpose and research. The primary goals of the ISS are to conduct scientific research in microgravity, demonstrate technologies for long-duration human spaceflight, and foster international collaboration in space exploration. Microgravity research. The unique microgravity environment of the ISS allows scientists to conduct experiments that are not possible on Earth. Research areas include biology, human physiology, materials science, fluid dynamics, and combustion. Studying phenomena in microgravity provides insights into fundamental scientific principles and potential applications in fields such as medicine, materials development, and environmental monitoring. Technology demonstration. The ISS serves as a testbed for new technologies and systems required for long-duration space missions, such as life support systems, spacecraft docking and rendezvous procedures, and radiation shielding. These technologies are essential for future exploration missions to the Moon, Mars, and beyond. Earth and space observation. The ISS is equipped with external payloads and instruments for Earth observation, monitoring natural disasters, climate change, and environmental processes. It also provides a platform for observing celestial phenomena and space weather. Crew and operations. The ISS is typically crewed by international teams of astronauts and cosmonauts who live and work on the station for missions lasting about 6 months. Crew members conduct scientific experiments, maintain station systems, and perform spacewalks, extravehicular activities, EVAs, to repair and upgrade external components. International collaboration. The ISS is a symbol of international cooperation in space exploration, involving space agencies from the United States, NASA, Russia, Roscosmos, Europe, ESA, Japan, JAXA, and Canada, CSA. Each partner contributes modules, resources, and scientific experiments, and shares operational responsibilities for maintaining the station. Mission control. The ISS is operated from multiple control centers around the world, including NASA's Johnson Space Center in Houston, Texas, US, and Roscosmos Mission Control Center near Moscow, Russia. These centers oversee station operations, coordinate scientific activities, and support crew members during their missions. Future and legacy. As of now, the ISS continues to operate as a vital platform for scientific research and international cooperation in space. However, plans are underway for its eventual transition to commercial operations and for the development of future space stations and exploration missions. Commercial utilization. NASA and its international partners are working with commercial companies to promote the use of the ISS for commercial research, technology development, and private astronaut missions. This initiative aims to stimulate economic growth in low Earth orbit and enable broader participation in space activities. Exploration goals. The ISS serves as a stepping stone for future exploration missions beyond low Earth orbit, including missions to the Moon under NASA's Artemis program and crewed missions to Mars in the coming decades. Lessons learned from operating the ISS inform the development of technologies and strategies for these ambitious exploration goals. In summary, the International Space Station represents a pinnacle of human achievement in space exploration, scientific research, and international collaboration. It continues to advance our understanding of space and contribute to technological innovations that benefit life on Earth and pave the way for future missions into deep space. Asteroids are small rocky or metallic objects that orbit the Sun, primarily located in the asteroid belt between Mars and Jupiter, though they can also be found throughout the solar system. Here's an overview of asteroids in our solar system. Types of asteroids. Asteroids can be classified into several types based on their composition, location, and characteristics. C-type carbonaceous. These asteroids are the most common type and are rich in carbon compounds, silicates, and hydrated minerals. They are found primarily in the outer regions of the asteroid belt. C-type asteroids are dark in color and thought to be primitive remnants from the early solar system. S-type silicaceous. S-type asteroids are composed mainly of silicate materials and nickel iron. They are found in the inner asteroid belt and tend to be brighter and more reflective than C-type asteroids. These asteroids are believed to have undergone differentiation, where dense materials sank to their cores during their formation. M-type metallic. Metallic asteroids are primarily composed of nickel iron. They are often found in the middle region of the asteroid belt. M-type asteroids are thought to be remnants of differentiated planetesimals or fragments of larger bodies that broke apart. V-type vestoid. Vestoids are a subgroup of V-type asteroids located in the inner asteroid belt. They are characterized by their basaltic composition and are believed to originate from the large asteroid Vesta. Vestoids have been identified through spectral analysis and are among the few asteroids for which we have direct samples, via meteorites. Trojans. Trojans are asteroids that share an orbit with a larger planet, typically located at stable Lagrange points, leading or trailing the planet by 60 degrees. Jupiter has the largest population of Trojans, but they are also found near other planets. These asteroids have stable orbits due to gravitational resonance with the planet they accompany. Distribution and characteristics. Main asteroid belt. The majority of asteroids are located in the asteroid belt between Mars and Jupiter. This region contains hundreds of thousands of asteroids, ranging in size from small boulders to large bodies several hundred kilometers in diameter. Near-Earth asteroids. NEAs, some asteroids have orbits that bring them close to Earth's orbit. These near-Earth asteroids, NEAs, pose a potential impact hazard and are closely monitored by astronomers. Some NEAs are also considered candidates for future space exploration missions due to their accessibility. Trojan asteroids. As mentioned, Trojans are asteroids that share an orbit with a planet. They are found in stable regions where gravitational forces balance out, making them relatively stable over long periods. Trans-Neptunian objects, TNOs beyond the orbit of Neptune. There are other populations of small icy bodies, including Pluto and its moons, which are considered part of the Kuiper Belt. Some of these objects, like Pluto, are large enough to be considered dwarf planets rather than asteroids. Exploration and study. Space missions. Several space missions have explored asteroids up close, providing valuable data and samples. Examples include NASA's OSIRIS-RX mission, which collected samples from the asteroid Bennu, and Japan's Hayabusa 2 mission, which returned samples from the asteroid Ryugu. These missions help scientists study asteroid composition, structure, and history. Impact hazard. Understanding asteroid orbits and compositions is crucial for assessing potential impact hazards and developing strategies for planetary defense. Techniques such as asteroid deflection and impact mitigation are actively studied to protect Earth from potential asteroid impacts. Scientific value. Asteroids are considered remnants from the early solar system and provide clues about its formation and evolution. Studying their composition and structure can shed light on processes such as planetary differentiation, impact cratering, and the delivery of water and organic materials to Earth. In summary, asteroids are diverse and abundant objects in our solar system, ranging from small rocky bodies to large metallic asteroids. They play a crucial role in understanding the solar system's history, potential impact hazards, and future exploration opportunities.